Hello everyone. Today I am Shishi. Today I'm going to introduce you all to the topic called the multiplicative group of integers modulo p. Welcome to a journey into the fascinating world of abstract algebra, specifically focusing on the multiplicative group of integers modulo p. This presentation will be covered the fundamental concepts of modular attachments and arithmetic and group theory, leading us to understand the properties and applications of ZP, a cornerstone in the uh, modern cytography and number of theories. Defining the multiplicative group of integers modulo p. The multiplicative group of integers modulo p, denoted as zp, consists of the set of integers 1 to p minus 1 under the operations of multiplicative operations of multiplication modulo p, where p is prime number. Its fundamental concept is abstract algebra, forming basic for many uh, cytographic algorithm. The group is specifically defined for prime moduli because prime numbers guarantee that every non element has multiplicative inverse, which is a crucial property for a group. Understanding ZP requires a grasp of modulo arithmetic where numbers wrap around upon reaching a certain value. The modulus, for example, the modulo 5 comma 3 into 4 is equals to 12, which is 2 mod 5. This se- seemingly simple structure holds profound mathematical significance. Properties of ZP: closure, associative identities, and inverse. For a set with operations to be considered a group, satisfy for axioms: closure, uh, associativity, existence of an identity element, and existence of an inverse for every element ZP perfectly fulfill these requirements. Closure ensures that multiplying any two elements within the set results in another element within the set. Associative means the group of operations grouping of operations does not affect the result. The identity element is 1 as any number multiplied by 1. Mod p remains itself crucially because p is prime. Every element a in zp has unique multiplicative inverse b, such that a into b is equals to 1 mod p, making ZP a cyclic group. Exploring primitive roots of modulo p. A primitive root of modulo p is an integer such that every integer in ZP can be expressed as the power of g modulo p. In simpler terms, G generates all the elements of the group ZP. The properties um, incre- incredibly important as it gives ZP a cyclic structure, meaning the group can be generated by a single element. Not all numbers can be primitive roots. For a number G to be primitive root modulo P, its order must be k to the power k, g to the power k is equals to 1 mod p must be equal to phi p is equals to p minus 1. The existence of the primitive roots is guaranteed for the prime numbers, making them a crucial aspect of ZP and its applications in the number of theory of cytography. Example of ZP for a small prime numbers. Let us illustrate ZP with some small prime numbers to solidify our understanding. These examples dominate how the elements behave under multiplication modulo p and how the group properties hold truth. For Z5, elements are 1, 2, 3, 4. Take let's take g is equals to 2 the power of 2 modulo phi r 20 to the power 1 and is equals to 2, and 20 to the power 2 is equals to 4, 2 to the power 3 is equals to 8, and then 2 to the power 4 is equals to 16. Since 1 and 2 generate all the elements, 2 is a primitive root. The systematic exploration helps in understanding the structure and cyclic nature of the groups. For example, Z3 operation Z into 1, 1 into 2, and then 2 into 1, Z5, 2 into 1, 4 into 1, 2 into 3, 4 into 3, and then 3 into 5 is equals to 1, 2 into 4 is equals to 1. I'm concluding my presentation after giving an example. Please do like, share my video. Thank you. Bye.